Hello everyone, this is part 2 video on the topic surface chemistry. In this video we look at the concept of adsorption isotherms, which will explain the relation of extent of adsorption on pressure in case of adsorption of gases and concentration in case of adsorption of solute. And also we look at the applications of the industrial and general applications of the adsorption. So what is an adsorption isotherm? From the word isotherm, we look at the phenomena at a fixed temperature. So adsorption isotherms are basically the analysis that we do which depict the relation between pressure of the gases on extent of adsorption at a constant temperature. So that is why the word isotherm has come. So we look at how the pressure of the gas, so we talk about, let us say, the adsorption of gas particles on surface of a solid, or the adsorption of gas particles on the surface of a liquid. So we'll see how the pressure of the gas will affect the extent of adsorption. So we'll see how do we measure the extent of adsorption also. So this is what we look at in terms of the adsorption isotherm. And in case of the adsorption of solute, if say for example we have a solution where the solute particles are going to get adsorbed on surface of the solid, there we will talk the relation between concentration of the solute to the extent of adsorption. That also we will study in the adsorption isotherms. First, how do we measure the extent of adsorption? So it is measured as the quantity of the gas adsorbed by unit mass of the adsorbent. So essentially we look at as the ratio of mass of the adsorbate divided by the mass of the adsorbent. So this is how we will measure the extent of adsorption. So we are going to see how the extent of adsorption is going to be affected by the pressure in case of adsorption of gases, and how it is going to be affected by the concentration in case of the adsorption of the solute. And we have two adsorption isotherm analysis. One is the empirical one, which we call as the Freundlich adsorption isotherm, named after the scientist, and the theoretical one, which is the Langmuir Expression isotherm. So mainly the Freundlich adsorption isotherm, this is defined for the physical adsorption or physisorption, and the Langmuir is defined for the chemical adsorption or the chemisorption. Freundlich is more of an empirical formula based analysis, and the Langmuir adsorption isotherm is based upon certain theoretical assumptions. Now when we talk about the Freundlich adsorption isotherm, it is an empirical isotherm which considers that the adsorbate will form a single layer on the surface of the adsorbent. So the extent of adsorption is going to be eventually limited, and this is different from the general phenomena of physical adsorption, because general phenomena of physical adsorption is a multi-layer phenomena. So we even talked about this in the properties of the physical adsorption, but here the Freundlich adsorption isotherm considers that there is only going to be a one layer of adsorbate on the surface of the adsorbent. And the empirical formula for the extent of adsorption and pressure relation is given by x by m is equal to k into p power 1 by n. Here x will be the weight of the gas that is getting adsorbed, and m is the mass of the adsorbent. Both are measured at a particular pressure p. So here the x by m will be representing the amount of gas adsorbed per unit mass of the adsorbent. So that is the extent of adsorption. And k and n will be the constants. So they depend upon the nature of adsorbate and adsorbent. Not only that, they are also a function of temperature. In fact, one of the limitations of the Freundlich adsorption isotherm is that why the values of k and n will change with regard to temperature, the isotherm could not give any theoretical explanation for that. So if you look at the value of n, the value of n will be more than or equal to 1. So as the pressure change happens, the value of n also will be changing. So this is another limitation of the Freundlich adsorption isotherm, where the reason for the change in the value of n also is not being explained with a theoretical reasoning, because the isotherm is merely an empirical relation between the extent of adsorption and the pressure. So this expression we can even change it into the logarithmic form, which we use for doing the graphical analysis, etc. So if you look at the x by m is equal to k into p power 1 by n, this equation, we take a logarithm on both sides, we'll have log of x by m is equal to log of k into p power 1 by n. So we look at it like log of a into b, we can write it as log k plus log of p power 1 by n. So if you have a logarithm of any number power something, the power will come to the front of the logarithm. So we'll have log k, log x by m is equal to log k plus 1 by n into log p. So this is the logarithmic form of the Freundlich adsorption isotherm. And in this, since the value of n will change from 1 to infinity, so as n goes to infinity, 1 by n will go to 0. So as n goes to infinity, 1 by n will be going to 0. So the range of 1 by n will be between 0 to 1. So this is about the Freundlich adsorption isotherm. And we can look at the graphical representation of it over here. Like, at low pressure, the 1 by, since n value will be equal to 1, 1 by n also will be 1. So we'll see that the relation will be x by m is equal to k p power 1 by 1, which is k into p. So the relation will be a proportional relation. We can see almost like a straight line. And at very high pressure, so when we go pressure beyond the saturation pressure, what we see is x by m will be independent of pressure. So there we explain it by taking the value of n to be very large. Thereby 1 by n will be approaching 0, and the relation will be x by m is equal to k into p power 0, which is independent of the pressure. Now in the moderate pressure range, we'll see that x by m will be proportional to p power 1 by n. So we can see that as the pressure is changing, the value of 1 by n is changing, and hence the slope of the graph also will change. So this is how we look at the empirical relation between the extent of adsorption and the pressure. And if you look at how the extent of adsorption is affected by the temperature, because we talked about it, generally the adsorption, if temperature is increased, more so particularly in case of the physical adsorption, temperature is increased means that will give more energy for the particles, and the particles will move away from the surface. So the extent of adsorption will decrease. So we see here T1 is more than T2 is more than T3. At a particular pressure, if you look at the extent of adsorption for T1 is the least, means as the temperature is increasing, the extent of adsorption will be decreasing. So this is about the Freundlich adsorption isotherm. Talking about the limitations of it, one, this isotherm is only for a certain range of pressure. We've seen the graph, the relation analysis is only limited between low pressure value to the saturation pressure range. After that, the dependency of pressure on the extent of adsorption is not being explained. And the constant k and n, they vary with temperature. So for this also there is no theoretical explanation as to how or why they are changing with respect to temperature. And the Freundlich adsorption isotherm, as we have been talking about, it's purely empirical formula. So the reason for the change in the value of n, the theoretical explanation for that is not being provided. So these are the limitations of the, and this one is mainly for the physical adsorption. So these are the limitations of the Freundlich adsorption isotherm. Now this is the point that we even talked about when we have discussed the differences between the physical adsorption and chemical adsorption. In the first part of the video in the chapter, we discussed about it. So we said both physical adsorption and chemical adsorption are negative enthalpy process. Delta H will be negative. Now as per the equilibrium phenomena of Le-Chatelier principles, if for any process delta H is negative, means high temperature, it will push the phenomena or the process in the backward direction. So whether it is the physical adsorption or chemical adsorption, high temperature is not favorable. But if you look at the physical adsorption, it is pretty straightforward. As temperature is increasing, we see that the x by m value is keep on decreasing. But that is not the case in the case of chemical adsorption. We see that chemical adsorption, initially x by m value is increasing with temperature. Once it is reaching the peak or the highest, then after that it is keep on decreasing. Now this is happening because the initial increase is happening because chemical adsorption is more like a chemical reaction, and this requires the activation energy. So initially when we are increasing temperature, what essentially is happening is more and more molecules are able to obtain the activation energy, and hence they will get adsorbed onto the surface. So the initial increase in the extent of adsorption is because of the more and more molecules getting the activation energy. And once we reach certain temperature range where almost all the available molecules are able to reach the activation energy range, after that what we see is, since this is also negative enthalpy process, if we keep on increasing temperature means the extent of adsorption will be decreasing. Why? Because the particles will on the surface of, if you look at the gas particles getting adsorbed on the surface of solid, the particles will have so much energy that they will start moving away. So this is about the dependency of the extent of adsorption on temperature. So there is a slight difference between the physical adsorption and the chemical adsorption, but at a very high temperature range for both of them it is not favorable. Now looking at the second one, which is the Langmuir Expression isotherm, which we generally use for the case of the chemical adsorption or chemisorption, which is based upon certain theoretical assumptions. Now if you look at the important assumptions, this is based upon the idea that the adsorbed gas layer is only one molecule thick, means it is a mono layer phenomena. So this is in line with the chemisorption as such, because chemisorption is a single layer phenomena, and the adsorption is seen as happening in two opposing processes or two opposing phenomena. So one, if you look at the gas particles coming and reaching surface, this is more like condensation of the gas, and second one is when the gas particles are going away from surface, this is more like evaporation. So we see it like there are two opposing phenomena. One is the condensation and second is the evaporation. And if you look at the rate of condensation of a gas, then this will be proportional to the number of unoccupied surface, or the unoccupied surface area, number of sites of unoccupied surface, or the surface area total value itself. So if you look at adsorption, it is mainly decided by the surface area, because it is a surface phenomena. More the available surface area, more will be the extent of adsorption. So the rate of condensation of a gas is proportional to the unoccupied surface area, which means if some part of the area is already occupied, the remaining available area will decide the rate of condensation, while the rate of evaporation is proportional to the covered surface. So covered surface will basically be the surface that is already occupied by the gas particles. So we have the condensation equivalent and the evaporation equivalent. The equilibrium stage will be reached eventually where the rate of condensation will be equal to rate of evaporation. And here pressure will play a major role, because as we increase the pressure, then if you look at the overall process, increase of pressure will push the phenomena more towards the forward direction, means there is going to be more of condensation. So if you look at the Le-Chatelet principle, if you have a substance changing from gas to liquid or gas to solid for that matter, then for this, if pressure is increasing, means as per the Le-Chatelet principle, the process will move in a direction where the number of gas particles will get lower, and it has to move in the forward direction, means it is going to be a favorable condition for the adsorption. And this is going to be happening till all the surface area is covered. So there is a limitation to which the adsorption can happen. So this is how the Langmuir adsorption isotherm is able to theoretically explain the possibility of reaching the saturation, and also how the pressure is affecting the extent of adsorption. So if you look at the Langmuir expression is x by m is equal to AP by 1 plus BP, where x is the mass of the gas or the adsorbent, m is the mass of the adsorbent, p is the pressure we are looking at, and a and b will be the Langmuir parameters. So we'll see how this expression we will be able to analyze. If we talk about very low pressure, so where the value of BP will be less, then in the denominator the 1 plus BP term, since BP is very lesser than 1, we can approximate it to 1. So thereby we have x by m will be equal to just numerator part, a into p. So at low pressure we see that x by m is proportional to pressure. This is able to explain the common observation. And at very high pressure, BP value is going to be very high in comparison to 1. So BP value is very high in comparison to 1. Denominator 1 plus BP, we can write it as almost BP. So P and P will be cancelled, x by m will be A by B. So we are reaching the constant or the saturation value. And if you look at the moderate pressure, the relation is going to be x by m is equal to AP by 1 plus BP. So this way, the Langmuir adsorption isotherm is also able to explain how the saturation or the maximum possible value for the extent of adsorption is reached at high pressure range, and at low pressure range why the extent of adsorption is proportional to the pressure value. Looking at the graphical representation of the Langmuir adsorption isotherm, so here x by m is equal to AP by 1 plus BP. We just do some small rearrangement. So we bring the P to the LHS, it will come to the denominator. So what we have is x by m by P is equal to A by 1 plus BP. We'll take a reciprocal of it, and what we have is LHS P by x by m will be equal to 1 plus BP by A. We'll split this as first term 1 by A, second term is B by A into P. So we look at this, this P divided by x by m is like the y coordinate. So we're taking as a y coordinate. Will be equal to C plus, this is like m into x. So the x coordinate is pressure. The value of m slope here is B by A. Slope of this line is, this graph is going to be a straight line. So the graph between P on the x-axis and P by x by m on the y-axis is going to be a straight line. Slope of the straight line is B by A, and the value of C here represents the y-intercept. So the value of P by x by m when the pressure is very less. So the y-intercept value here, C, which is equal to 1 by A. So this is how we look at the graphical representation of the Langmuir adsorption isotherm. Now the way to remember this is, we don't need to really by heart this one, but what we can do is just remember the Langmuir expression, x by m is equal to AP by 1 plus BP, and then see how we are going to rearrange. So we'll bring the pressure to the LHS and then take a reciprocal and split the terms. So this is about the Langmuir adsorption isotherm, which is also able to explain the observations, and this has the theoretical backup of the analysis or the observations. Now we have talked about the adsorption on the surface of solid or the surface of liquid by a gas. So that is why we have been considering the effect of pressure. But if you look at the adsorption of solute particles onto the surface of solid, there the extent of adsorption, x by m, is going to be determined by the concentration of the solute. So concentration, we will talk about generally the molar concentration. So in this case, what we will have is, for the Freundlich isotherm as well as for the Langmuir isotherm, we are going to have similar expressions, but the only difference will be wherever we have a pressure there, in this case we are going to be having the concentration. So the Freundlich relation will be x by m is equal to k C power 1 by m, where C will be the concentration. Remember, in the case of the gas absorption, we had x by m is equal to k into p power 1 by m. In the Langmuir adsorption isotherm, we will have x by m is equal to AC by 1 plus BC. So in the case of gases, we had AP by 1 plus BP. So we'll have similar expressions, but the only thing is, wherever we have pressure in case of gases, in case of solute, we are going to be having the molar concentration. So that is the difference between the adsorption of the gas and adsorption of a solute from solutions. Now coming to the important area of applications of adsorption. So we do get some theoretical questions in competitive examinations on this. So adsorption as such is a very common phenomena in terms of the daily life observations, as well as some very important industrial applications. As we talked about it in the first video, this adsorption is used for the production of high vacuum. So high vacuum basically means the region or space which has almost no gas particles. Now if you look at generally when we have a room and we are trying to create vacuum, we'll use a vacuum suction pump so to remove the air from the room, but still we'll have some traces of the air remaining, and these traces of the air, they can be adsorbed by the charcoal, and by that we will be able to create a very high vacuum. So generally when we have the normal vacuum pump, we will not be able to remove the traces of the air, but if we have the charcoal, then we will be able to create a very high vacuum where we will be able to remove even the small trace of the air particles. And the other common applications is the gas masks. So we have a combination of various adsorbents which is commercially called as activated charcoal. So activated charcoal is generally used in these gas masks, especially the coal mines and other mines where there will be the possibility of poisonous gases, like coal mines there will be a possibility of sulfur dioxide. So before people breathe in the gases will be made to go through the gas mask. So all these poisonous gases, they will get adsorbed on the activated charcoal, and the people will be able to breathe the pure air. So this is another application of the adsorption. And the common thing that we will see around us is we would have seen these packets of silica and aluminum gels. They are generally used for removing the moisture. So we do see them in some computer parts, etc. These silica gel will be coming in packets where they will be able to control the humidity. What they do is any air or the moisture in the atmosphere will get adsorbed on the surface of the silica. So this is another common application of controlling the humidity. Then talking about some industrial applications, we have removal of coloring matter from solutions. Animal charcoal, which will be really porous in nature. So remember, adsorption as such is a surface phenomenon. Porous materials, they will have more surface, and hence they will be effective adsorbent. So animal charcoal, which is produced from the charring of the animal parts, will be able to remove the colors from the solutions, especially the organic solutions, where they will be able to adsorb the coloring impurities, or we can say colored pigments. So like if you look at this example we even discussed in the first video, the raw sugar or sugarcane juice solution, it will be a little bit brownish tint, but when we drop some animal charcoal and then shake it, we'll see that the solution will become colorless. The reason is that the colored pigments are being adsorbed on the surface of the animal charcoal. This is very effective in case of the removal of color from the organic pigments. And we'll see that the names of the charcoal will come from the source. Like we'll say coconut charcoal. Coconut charcoal, in fact we'll talk about this in a little while. But yeah, coconut charcoal means it will come from the charring of the coconut. And we'll have sugarcane charcoal. So sugarcane charcoal will be coming from the charring of the sugarcane, the pulp. So the source is basically going to be the name for the respective charcoal. The other important industry application is the heterogeneous catalysis. In fact, that will be the next video in the chapter. Heterogeneous catalysis will basically be a phenomena where we have, say for example, the catalyst is a solid. We'll have the reacting substances which are in the either gas phase or in the solution phase. So that is when we will call the catalysis. The physical state of the catalyst and the reacting species will be different. That is when we'll call it as a heterogeneous catalysis. So heterogeneous catalysis is explained by the adsorption. So adsorption of reactants on the solid surface will increase the rate of the reaction. So this is the observation. And commonly, like most of the industrial manufacturing process, like the manufacture of ammonia in the Haber's process, we use iron as a catalyst. The contact process for the manufacture of sulfuric acid, and even the hydrogenation of oils where we use a nickel or a platinum or a palladium as a catalyst, all of this is based upon the idea of adsorption. So we'll see how the adsorption is able to increase the speed of the reaction when we go to the catalysis. But this is a common observation that the adsorption is the reason for the enhancing of the speed of the reaction. Now the other application is especially for the inert gases where it is difficult to separate them due to similarity in various of their properties and less chemical reactivity. What we see is that the inert gases can be separated from each other by using the difference in the degree of adsorption. So the gases, they have a difference in the degree of adsorption when they are getting adsorbed from charcoal or coconut charcoal particularly. We'll see that by using this relation, we will be able to separate the gases. So first we will have the gases that are getting adsorbed more. Initially for a lesser time, if we expose the gases mixture to the charcoal, predominantly the gas that is getting adsorbed more, that will be onto the surface of charcoal. And in the chamber, the finally leftover gas will be mainly the one that is getting least adsorbed. So using this phenomena, we will be able to separate the mixture of the inert gases. So these are some of the industrial applications of the adsorption. And not just that, we even have applications in medicinal purposes and even some the metallurgy industry also. So if you look at some of the drugs that are used to kill organisms or germs, they achieve this by getting adsorbed on the surface of the organism or the germ. So if you have a germ, the drug will go and get adsorbed on the surface of the germ and it will start having its activity. So this is a process that happens in certain drug applications. And the metallurgical process which we will talk in the metallurgy chapter, of course, that is based upon the idea of adsorption is froth flotation. Froth flotation is a method that we use to enrich or concentrate the low-grade sulfide ore. Low-grade sulfide ore means along with the particular ore. So we have so many common sulfide ores like zinc sulfide or lead sulfide. These are generally the sulfide ores that we will be using. Even copper sulfide is there. So low-grade sulfide ore which is having the general impurities like silica or other earthy matter, the gangue particles. To remove these gangue particles from the sulfide ore by using the froth flotation method, here the adsorption phenomena comes to use. So in a froth flotation chamber, what we'll have is we'll have the water into which the ore particles are dropped, and we'll pour pine oil, and when air is supplied with an stirring rod, what we see is there is going to be a froth that is getting formed, and the oil particles they will be able to wet the ore particles better. Means there is going to be adsorption of oil particles to the ore, and which will be carried along with the foam, whereas the remaining gangue particles will be settling as a deposit at the bottom of the chamber. So the adsorption of oil particles on the surface of the lead ore particles is the reason for the ore particles to come along with the froth, and we can easily separate that froth out and then remove the ore particles separate. So this method is based upon the idea of adsorption of oil particles onto the surface of the sulfide ore. So this is the metallurgical process for flotation based upon the idea of adsorption. So these are the applications of the adsorption. So we have seen there are some very common observations or applications that we see in general daily life around us, and there are some important industrial applications including the catalysis, and we have even applications in metallurgy as well as the drug industry. We even have some laboratory applications, especially when we talk about certain reactions where we need to understand the end point of the reaction. So whether it is the acid-base reactions or any reaction for that matter, we use what we call as indicator. Now we have the concept of adsorption indicator. So what is adsorption indicator? Generally, even when we are using the acid-based titrations, we use indicators, phenolphthalein, methyl orange. Basically they will create a color change which is noticeable, and hence we will be able to clearly observe when the end point is happening. So if you look at surfaces of certain precipitates such as silver halide, they have the property of adsorbing some dyes like eosine, fluorescein. Basically these are the organic dyes which are consisting of nucleic acids, and when they adsorb, they will be able to produce characteristic color at the end point. So the color change is going to be happening because of the adsorption, and that is how we will be able to use the adsorption as an indicator. Now even one of the very important laboratory method for both separation as well as for the analysis is the chromatographic analysis. So we have here the sample column chromatography, where if we have a substance which we call as the mobile phase, which is generally the mixture which we want to separate or which we want to analyze, will be poured into this column. The column will be packed with what we call as stationary phase, and the components of the mobile phase will get adsorbed. So if you see, let us say for example the component C, which is orange color, is getting adsorbed more, so it will be at the top, and component B or the reactant B is going to be at the bottom because it is getting adsorbed less, so it will keep going down. So the components that are getting adsorbed more will stay at the top, and the components that are not getting adsorbed will keep going down. So the column chromatography or the chromatography methods, they are named because of the color separation. You can see that the components will be getting separated based upon the color, but the idea is that the ones that are getting adsorbed more, they will be able to stay at the top of the column. The ones that are getting adsorbed less, they will keep going to the bottom of the column. And this phenomena is used in both the industrial applications as well as the analytical methods. So analytical methods means the qualitative analysis as well as the quantitative analysis, and even in terms of the separation methods. So this is about the applications of the adsorption in laboratory level. So this is about overall applications of the adsorption. So this will be the end of part 2 video, and we'll see in the part 3. So in part 3 we'll mainly talk about the catalysis.